All right, let's get right into it. If you've got an embedded C++ interview coming up, especially for a fresher role, this is for you. We're going to build your study guide focusing only on the stuff I am almost certain they're going to ask you. No fluff, just the high-impact knowledge you absolutely need. You know that feeling, right? You're staring at this absolute mountain of C++ concepts, and you have no idea where to even start studying. It's a lot. But don't worry, we're going to cut right through all that noise. I'm going to give you a roadmap straight to the questions that really matter for embedded systems. So let's dive in. Okay, first things first. Every single C++ conversation you're ever going to have, especially in an interview, it's going to start right here with the 4 pillars of object-oriented programming. You've got to know these cold. Seriously, this isn't just abstract theory. This is the basic language you'll be expected to speak from day one. And here they are, the big 4: abstraction, encapsulation, inheritance, and polymorphism. We're going to knock out the first 3 right now. And that last one, polymorphism, well, it's so important, it's so juicy, we're going to save it for its own special section a little later. So let's break these down. So, abstraction. When an interviewer asks for an example, here's what you say. Think about the public functions of a class. They're like the buttons on your TV remote. You know that the volume button makes it louder, but you don't need to know or care about the complex circuitry inside that makes it happen. That's abstraction. It's all about a simple interface hiding away the messy details. Next up, encapsulation. And this one is huge for embedded systems. The whole point is protecting your data. You bundle the data and the code that's allowed to touch that data together in a neat little package, a class. This puts a protective wall around your data, which is absolutely critical when a random bit flip could cause a catastrophic failure. And pillar number 3 for now is inheritance. This is the classic is-a relationship you've probably heard about. For instance, a temperature sensor is a kind of sensor. And why is this so great? It's all about not repeating yourself. You write the generic sensor code one time, and then all your specific sensor types can just reuse it. It's a huge time saver. Okay, we've covered the OLP basics. Now let's get into the stuff where embedded interviews get really serious. Memory. When you're working with tiny microcontrollers, how you manage every single byte of memory is everything. This is where you can really show an interviewer that you know your stuff.
Get ready for this one, because you are gonna hear it. What's the difference between a pointer and a reference? The key thing to remember is the trade-off: safety versus flexibility. A reference is just another name for an existing variable. It's safer, it can't be null. A pointer, though, holds a raw memory address. It's way more flexible, way more powerful, but also way more dangerous if you're not careful.
And another classic, new versus malloc. Why did C++ invent new when we already had malloc? It comes down to one word: constructors. See, new doesn't just grab a chunk of memory. It knows about objects. It calls the constructor to properly bring your object to life. And when you delete it, it calls the destructor. It respects the object's entire life cycle in a way malloc and free just can't. All right, let's talk about a couple of keywords that are more than just syntax. They're like a secret code that signals your intent as a programmer. I'm talking about const and static. You will absolutely be tested on these. Nailing them shows you're not just trying to make code work, you're trying to make it safe and robust. So, static. The easiest way to wrap your head around it is this. Static things belong to the class blueprint, not to any individual house built from that blueprint. So a static variable is like a master counter of how many houses were built, shared by everyone. And a static function? You can call it even before you've built a single house. And now for the dreaded const pointer puzzle. This one trips up so many people, but here's a pro tip. Just read the declaration backwards, from right to left. So, int star const ptr becomes ptr is a const pointer to an int. Constant par ptr is a pointer to an int that is const. If you can remember that little trick, you've got this question locked down. But why all the fuss about const? Well, in the embedded world, const is your best friend. It's a promise. It's a contract you make with the compiler that says, I promise I will not change this thing, and the compiler will actually stop you if you try. This is so important when you're dealing with things like hardware registers that you must not change by accident. Okay, remember that 4th pillar we saved? Well, it's time for the main event, polymorphism. It literally means many forms, and it's where C++ gets incredibly powerful. This whole concept is made possible by something called late binding, and yeah, You can pretty much guarantee this is coming up in the interview. So the difference here is all about when a decision gets made. With static binding, the compiler figures out exactly which function to call way ahead of time, before the program even runs. It's fast and simple. But dynamic binding, that's where the magic is. The program waits until the very last second, at runtime, to decide which function to call. It lets a generic sensor pointer correctly call the specific read function for a temperature sensor. Now, a good interviewer won't stop there. They'll say, okay, that's what it is, but how does it actually work under the hood? If you can answer this next part, you're going to seriously impress them. The secret involves two hidden things the compiler adds for you, the v-pointer and the v-table. It's actually a pretty elegant system. Think of it like this. Every object gets a secret little pointer, the v-pointer. That pointer points to an address book for its class, the v-table. The v-table is just a list of where all the correct functions live. So when you make a virtual call, the code just follows the pointer, looks up the right address in the book, and makes the call. Simple as that. Okay, one last critical point on this topic. Virtual destructors. And please remember this one. If you forget to make your base class destructor virtual, you will cause memory leaks. It's a classic textbook C++ bug, which means, you guessed it, it's a classic interview question. They're checking to see if you know how to avoid this trap. So look, we've gone through the what of all these core concepts. That's step one. But to truly nail that interview, you have to be ready for the why. Why is polymorphism perfect for managing different hardware drivers? Why is const correctness so critical for safety? If you can connect these concepts to real-world embedded problems, you won't just pass the interview, you will absolutely ace it. Now go get 'em. Good luck.